I'm Austin Elliott. I'm a postdoctoral researcher in the Oxford Department of Earth Sciences. I research earthquakes, and I'm going to talk to you today about how we understand earthquake hazards and how we investigate risks in hazardous parts of the world using satellite observation of the planet. To begin with, earthquakes have been observed and cataloged for the better part of a century now, rather uniformly. And what we find is that they concentrate in particular zones of the world. These are the crustal plate boundaries. You'll know them as tectonic plates. And they highlight familiar areas such as Indonesia and Japan, Nepal and the Himalayas, and a belt extending from the Himalayan front all the way through the Alps in Central Europe. What we can do, in addition to understanding the distribution of the earthquakes, is map out the strain fields, the deformation of the crust of the planet. What we find when we look at where the crust is deforming, bending, and crumpling is that it highlights these belts that match very well where we find the earthquakes. That's, of course, because the earthquakes are caused by the deformation of the crustal plates. Naturally, this map of the global strain field, the high bright colors represent the more rapid deformation of the crust, are coincident with areas with high seismic hazard, lots of earthquakes, and when we look at a global seismic hazard map of the world, we see these areas highlighted brightly. Again, the familiar areas: Indonesia, Japan, the North Anatolian Fault through Turkey, which has produced a series of devastating earthquakes over the 20th century. The high seismic hazard zones of Italy, Greece, and Eastern Africa. But what I'd like to point out is that while many of the earthquakes and much of the seismic hazard is concentrated around these belts of plate boundaries, in Central Asia, there's this very broad region of deformation that extends all the way from the Himalayan mountain front well into Mongolia, Kyrgyzstan, Kazakhstan. And in fact, what you can see is that some of the highest seismic hazard on the planet is centered around the small mountainous nation of Kyrgyzstan and its border with southern Kazakhstan. We go out to study these highly hazardous areas in order to understand the earthquakes that happen there, how they happen, how frequently they happen, where they may happen next, and what the impact is when they do happen. The reason that Kyrgyzstan and southern Kazakhstan have such high seismic hazard is that they lie along the Tian Shan mountain belt. This is a region of high, several thousand meter mountain peaks that separates the dusty deserts of China from the flat Kazakh platform extending out to the north. As you can see in this image, it's an extensive mountain belt, and the mountains have this alignment east-west. This is Lake Issyk-Kul. It's the defining feature of the country of Kyrgyzstan. These mountains are the manifestation of the crumpling crust here, where the convergence between the Indian plate and the Eurasian plate produces this crumpled belt of compressing crust. Here, at the very leading edge of this mountain belt, is the city of Almaty. It's the largest city in Kazakhstan, housing 2.5 million people. In the past century, Almaty, earlier known as Verny, has been hit by a series of large earthquakes. In fact, in the late 1800s, they had a devastating sequence, one every 2 years, that included a magnitude 7, magnitude 7.3, and culminated with this magnitude 8.3 massive earthquake that devastated the city that existed at the time. Just 2 decades later, another magnitude 8.0 earthquake hit the even larger city that had been rebuilt in its place. This sequence of earthquakes is really important because now, a century later, this is what Almaty looks like. It's home to 2.5 million people, full of high-rises, huge development, and it still faces this same seismic risk from the same active faults. So we go out to try and understand the nature of the earthquakes that hit it in the past in order to understand what may happen in the future. Here we have another view of the Tian Shan mountain range. Lake Issyk-Kul in the middle, and Almaty is just at the front side of the mountains there on the north side of the lake. The way that we go about trying to understand the earthquakes is to look at their record in the landscape and the terrain around them. Several of these earthquakes were before instrumental seismology, and so this is one of our only ways that we can still access the details of what happened during these big seismic events. The way that we derive information about the landscape is to look at terrain models, elevation maps, which we can derive using satellite imagery. The way that this works is the same way that you see in 3 dimensions. This is a classic satellite image looking directly down at the planet. But as a satellite flies overhead and passes, it has different vantage points of the Earth. And so the view from a passing satellite would look something like this. As we step back and forth through these images, you can clearly get a sense for the 3-dimensionality of this river valley. This information is used by the satellites. We do calculations that locate correlative portions of each image and identify their height above some uniform surface. This is conceptually what that process looks like. The satellite flies over, gaining different vantage points of the ground. From those different vantages, we can calculate the elevation of all the points within those images. From this, we derive detailed maps of the ground surface. These maps are down to sub-meter resolution, so we can pick out features including bushes, trees, and of course the individual scarps and cracks left by these earthquakes a century or more ago. What that allows us to do is take a scene like this, beautiful satellite view of a mountain, a ridge crest in a mountain range. What we can do using stereo satellite imagery is derive a 3D model of that. This detailed model allows us to map out features, fractures, and cracks that run through the mountain range and represent the faulting that produces these earthquakes. Here's what we can derive using these detailed models. This is a map of the fault lines that have fractured the top of this mountain range. And along their lengths, there are small scarps, small offsets that represent what happened in the most recent earthquake in 1889. In order to get a better view of these individual fractures and really measure this in detail, we use our own, let's call them low-altitude satellites. So we go out with drones, quadcopter aircrafts with mounted cameras, or, barring suitable conditions or regulations for drones, we go out with a balloon strapped with a camera. We walk it along the landscape and derive a detailed model of a small portion of it using these same techniques and principles. What you see here is the path that we've walked out in the mountainous landscape of southern Kazakhstan that follows the trace of one of these fault lines that we've identified as having produced the 1889 earthquake. In detail, we can zoom in a little more, and we really see how this fault offset the landscape during the earthquake. This terrain model captures bushes, trees, individual features, as you can see here, and it also captures and allows us to quantify the offset in the landscape. So we can look at these features and make detailed measurements. In this case, what we find is that the ground slipped 8 to 10 meters during this earthquake. And that helps us corroborate the magnitude of the event. It also helps us understand the network of faults that ruptured together in order to produce this earthquake. And that gives us an idea of how they break in this and other similar events and may break in the future. So what we ultimately can do with these terrain models that we make is map out all of the threatening faults in this mountain range. Here we look at a digital elevation model that spans the northern range of the Tian Shan. Almaty is highlighted there at the mountain front. And what we've been able to do is map out all of the faults that have produced these mountain ranges over time, and through multiple hundreds or thousands of earthquakes, and present potential risks for earthquakes in the future. In particular, we've identified the nature of some of the earthquakes that happen here, including the large magnitude 8.3 earthquake in 1889, portions of which I just showed you. Highlighted here are the faults that ruptured to produce that earthquake. It's a complicated Z-shaped network of faults that includes more than just a single strand. This is important for calculating seismic hazards in the future, as some of the faults may in fact join together in producing larger earthquakes than we might expect. The earthquake 2 decades later, in 1911, ruptured this series of faults along the same fault zone, but another complex pattern of ruptures. Taken together, these are 2 large, complicated earthquakes in the middle of a vast network of faults in this deforming region. What that shows is that the faults can work together, can sometimes rupture in large earthquakes with tens of meters of slip at one time, in much larger earthquakes than we might otherwise expect. By taking this approach and evaluating the faults this way, understanding the earthquakes that have happened and the other earthquakes that may happen along other faults in the system, we can map out this entire region of Central Asia and investigate each one of the many, many faults that are riddled through the crust here and produce earthquakes, which present a large hazard and increase the risk to these big cities along the ancient Silk Road through Central Asia.
Earthquake. Moderate shaking expected in 21 seconds.